A very good morning to one and all present over here. My name is Sanket Hedduri and I am a research assistant at the Crucible of Research and Innovation at PES University, Bengaluru, India. And I'll be presenting our work on noise and vibration analysis of a flux switching motor with segmental rotor. The co-authors of this study are Kishore MN, my colleague, and Dr. Suresh Nagesh, our mentor. So I'll briefly talk about why noise and vibrations come into play in an electric motor. So the branch which deals with predicting rotor vibration and containing the vibration levels under acceptable limits is called rotor dynamics. Now rotor dynamic imbalance in motors is caused due to a variety of factors, including but not limited to misalignments between the couplings or bearings to the motor, air gap eccentricity which is present between the stator and the rotor, oil whip, and also electromechanical interactions. Our study deals with the rotordynamic imbalance induced in a flux switching motor due to electromechanical interactions. The following equation is the generalized rotordynamics equation wherein u dot and u double dot are displacement, velocity and acceleration respectively. M, C, K are the mass damping stiffness matrices respectively. G is the skew symmetric gyroscopic matrix. B is the rotating damping matrix which changes the stiffness of the structure depending upon the change in rotational velocity, and F is the external force vector. Now our study concerns with putting the electromechanical interactions between the stator and the rotor in place of the external force and finding out the response of the system. Flux switching motor with segmental rotor is a new class of electric motor with both AC and DC windings on the stator. The rotor is devoid of any windings, and FSM with its high torque density, compactness, less heat production, and high ruggedness can prove to be an ideal motor topology to be used for the propulsion systems of electric vehicles. Now the construction of a flux switching motor FSM is fairly simple. It has a stator on which there are alternate coils of AC and DC, and then there is a rotor core on which rotor segments are installed. Now the rotor core is made up of non-magnetic steel, and the rotor segment is made up of magnetic steel. So what this ensures is that the incoming magnetic flux from the stator teeth will pass only through the rotor segments that are highlighted by the orange color. And what happens is that this gives rise to a very high torque density and lesser heat production because magnetic flux doesn't leak into the rotor core. We first started with the design of flux switching motor. Now this design was done from scratch using some standard parameters, and we chose the number of rotor segments to be 8. This was based on existing literature review that 8 rotor segments are better than any other number for reducing vibration. So after this we performed an electromagnetic analysis to find out the path of the magnetic flux taken from stator to the rotor, and then on optimization was done to prevent any magnetic flux leakage. We also ensured that magnetic saturation didn't take place in any of the materials, be it stator or the rotor segments. And then after this, after optimization, we input the electromagnetic forces acting from stator to the rotor for rotor dynamic analysis, and then the structure's response to this force was found out. This slide shows the input configurations for the simulations that we have performed. The motor that we designed was such that its rating was 1 kilowatt and its rated speed 3000 rpm. The number of stator poles that was chosen in the design was 12, and since the AC and DC coils are alternate on the stator poles, so there are 6 each of AC and DC excited coils. The number of rotor segments chosen was 8 to reduce vibration levels, and the AC and DC supply currents were 5 amperes each. The air gap maintained between the stator tooth and the rotor segments was 0.5 mm. The materials chosen for each of the parts are as following. For the rotor segments, we chose M36 electrical steel, rotor core, AISI 304 stainless steel, which is a non-electrical steel and doesn't let any magnetic flux in. Stator also is made up of M36 electrical steel and the windings of AWG12 copper. This is the finite element model of the 8-segment flux switching motor we built. It had 64,422 elements and 39,060 nodes. This image is a snapshot of the simulation result that we produced. We started out with the aim of design and efficiency optimization from the crude design that we started out with, and we wanted to provide a low reluctance path for magnetic flux lines flowing from the stator to the rotor segments. And also we wanted to prevent magnetic saturation. So for M36 electrical steel, the magnetic saturation limit is about 1.6 Teslas. So after optimizing the design, we saw that the magnetic flux on the stator and the rotor was below 1.44 Tesla on an average, and hence losses due to magnetic saturation were lowered. And as you can see, as is represented by the red arrows on the figure, this is the path which was taken by the magnetic flux lines after optimization. So there, after optimization, there was very less leakage of the same, and this resulted in an increased torque output and also simultaneously reduced vibration and noise levels. The maximum nodal EMF at any point on the rotor was found to be about 10 newtons, and the average absolute total EMF for this rotor was found out to be 75.86 newtons. Now let me talk about the rotor dynamic analysis of the rotor. So first we performed the modal analysis to find out the natural frequencies of the rotor. The first 6 modes of vibration were 0 or near 0, which actually verified the structural integrity of the finite element model. Now, as you can see in the table, that the frequencies, natural frequencies of the rotor are about 13,000 hertz. While this may seem to be unusually a very large number, it is to be kept in mind that this motor is actually very small. Uh, so if the rotor is considered as a cylinder, it has a diameter of around 5.5 centimeters and a length of 8 centimeter, and hence its mass is very low. And we know that natural frequency is inversely proportional to the square root of mass, and hence because of low mass, the natural frequencies of the rotor are so high. And if anyone wishes, you could email it to us, and we could send in the our hand calculations of for calculating the natural frequencies. For a practical world analysis and to reduce computational cost, we found out the response of the rotor for the operational frequency range of 0 to 50 Hz or 0 to 3000 RPM. And we found out that the rotor is very much safe in the operating region. Further, we found out the noise in form of sound pressure level due to the electromagnetic forces acting on the rotor segments. And we found out that the maximum sound pressure level was 101.49 dBA at a rotational velocity of 3000 RPM. Now it is to be kept in mind that the analysis was done for bare rotor, that was not connected physically to the whole motor through bearings. And if bearings were included in the calculation, they can greatly bring down the noise and vibration, as bearings are known to reduce the transmission of the same. Now, sound pressure level can also be further reduced by using acoustic padding inside the motor. We've almost come to the end of this presentation. So in conclusion, I'd like to tell you that we built a flux switching motor with 8 segments from scratch. electromagnetic analysis, and consequently design optimization was done on it to increase its efficiency and to reduce noise and vibrations. We also, in the end, found out the noise and vibration due to EMF on the optimized rotor design. Here is the list of references that we used throughout our study. So I'd like to thank each and every one of you who listened to this presentation so patiently, and I hope you enjoyed our study. If you have any questions, then please feel free to email me or Dr. Suresh Nagesh at the following email address, which is shown on this slide.